All right, on to chapter 3 and the main material of the course. So chapter 3 is all about matrices. Okay, section 1 is basic definitions and notation. Some long sections in this chapter. The whole chapter is about 100 pages of the book. And here in the beginning, I think the first 3 sections are particularly lengthy, but in section 3.1, a lot of this, though certainly a fair chunk of it isn't, familiar to you from sophomore linear algebra. So we'll deal with defining matrices and trace, and we won't deal with matrix products in this section, but we'll encounter eigenvalues, matrix products, determinants along the way in chapter 3. So this is the theory of matrices part, really. Okay, so section 3.1, definitions, notation. We'll see, again, many ideas from sophomore linear algebra: diagonal matrices, trace, minor matrices, cofactors, determinants. So we'll do determinants, I think, in this section. Our approach will be a little more sophisticated than it is in just sophomore linear algebra to the determinant stuff in particular. Okay. So we'll take A to be an n by m matrix, treating the columns of A as n vectors. The vector space generated by these column vectors is called a column space of matrix A, just like in sophomore linear algebra. Treating the rows as m vectors, it's not a square matrix. The vectors generated by these rows, treating these as a spanning set, is called a row space of A. So usual stuff, the span of the columns or the column space, the spans of the rows or the row space. The emphasis will more often go on the column space than the row space. It's because we'll mostly, but not exclusively, deal with row operations, and that's, in a sense, it's related to the columns of A in a more direct way, to be elaborated on at length. And you saw it in sophomore linear algebra as well. The column space is denoted the span of A, when you might think that's ambiguous. Why wouldn't that be the span of the rows? Why is it the span of the columns? As you know, both of those spaces are of the same dimension, and it'll follow one of these days that fundamental theorem of finite dimensional vector spaces, I'll call it. Hey, the row space and the column space, they're the same dimension, they're isomorphic vector spaces. But to be precise, when we write span A, we mean the column space of A. The span of A, the column space, it's sometimes called the range of A. This word manifold pops up. Not sure, I don't think we'll use that too much. The word range certainly is meaningful because if we were to treat multiplication by matrix A as a linear transformation, that would take us from Rn to Rm, if I'm thinking correctly about the dimensions. No, excuse me, take Rm into Rn. We could treat multiplication by A as a linear transformation between the appropriate dimension spaces. And then the range of that linear transformation would be the column space. Remember, when you take a matrix A and multiply it by a vector X, A times vector X, that gives you a linear combination of the columns of matrix A. You let that X range over all appropriate dimensioned input vectors, and that will generate the column space of A. If you think of multiplication by A as a linear transformation, then range is totally the appropriate term to use. Term manifold, that means a number of different things in a number of different settings. For us, we'll primarily stick with the term column space, but I'd argue range is a reasonable term. Okay, so we're effectively making a vector space out of matrices in some of these manipulations. If we take a matrix A, capital A with entries lowercase a sub ij, standard notation, define scalar multiplication, entry-wise define scalar C times matrix A as the matrix with entries C times a sub ij. Just multiply the constant on each of the entries of that matrix A. Probably use the term entry in reference to the numbers in a matrix. Components is more a word I'd use in the setting of vectors. I wouldn't argue too much if I wanted to use the term component in the setting of matrices, but that really is more of a vector term. So entry-wise is how we'll deal with these particular little manipulations. So you do the same thing you do with vectors. You put that scalar multiple on each of those numbers inside that thing. You want to add two matrices together as long as they're the same size. Do it entry-wise. Matrix A plus matrix B. Say matrix A has entries lowercase a sub ij. Matrix B has entries lowercase b sub ij. Add the corresponding entries together. Okay, well then if you can multiply by scalars and add these things together, that's what you do to vectors. So we could actually make vector spaces out of matrices, and we'll see a little bit of that in what follows. The diagonal elements of matrix A with entries a sub ij are the elements of the form a sub I for I equals 1 to the minimum of dimension m and dimension n. We didn't make an assumption following this notation here. We didn't make an assumption of a square matrix. So here's something a little bit different from sophomore linear algebra, where you probably only talked about diagonals for square matrices. Okay, we're talking about the a sub ii entries, and those make up the diagonal elements of a matrix A, whether it's square or not. Sometimes those diagonal elements together make up the diagonal, or this might be a new term to you, the principal diagonal, because we're going to talk about some kind of off-diagonal expressions as well. If we look at the elements a sub ij, where I is less than j, all right, so remember this is kind of I is the row, so it's how many times you've gone down. J is the column, how many times you've gone over. So when I say I is less than j, we've gone further over to the right than we have down in the matrix. Think about it. These entries a sub ij, where I is less than j, would be the entries above the diagonal elements. If I is greater than j, we've gone further down than we have over, and those are the elements below the diagonal. So it's got the obvious geometric interpretation that you're used to in terms of the locations of these entries. The elements a sub I comma I plus k, where we've chosen some fixed k, form what these guys call the kth codiagonal or the kth minor diagonal. So in addition to the principal diagonal, there's these other diagonals. When k equals 1, we're looking at the entries a sub I comma I plus 1. So these would be the entries that are all adjacent to and above the principal diagonal. If we took -1, k equals -1, these would be all the entries adjacent to and below the principal diagonal. Here's something a little bit new. Might not be a surprise to you to encounter this idea. But we're taking an n by m matrix A, the elements a sub I comma n plus 1 minus I, where I ranges from 1 to the minimum of m and n. It's called the skew diagonal elements of A. I guess we can collect them together and call them the skew diagonal. So there's a principal diagonal. There's these kind of codiagonal things. These all run in some sense from the upper left down to the lower right, as does the principal diagonal. Here, we're running in the other direction. Here, we're starting at, when I equals 1, we're starting at a sub I comma m. All right, so we're starting at the upper right and going to the lower left, instead of starting at the upper left and going to the lower right. So this is a back diagonal. I've informally called it before, but skew diagonal, that makes sense. It's the other diagonal of the matrix. Oh, and again, we're not requiring that we have square matrices. So these don't run really, you know, from one corner of the matrix to the other opposite corner, unless it happens to be a square matrix. A square matrix is said to be symmetric if A sub ij equals A sub ji for all indices I and j. Okay, of course, we'd have to have a square matrix to make sense out of this, or else we'd run out of i's before we run out of j's, or vice versa. So symmetric, maybe you've referred to this in the past as symmetric with respect to the main diagonal, principal diagonal. But it has the obvious kind of symmetry results that you're used to from sophomore linear algebra. Square matrix A is called skew symmetric if A sub ij equals negative A sub ji. So it's like a symmetric matrix, only all the entries below the diagonal have signs that differ by -1 from the entries above the main diagonal, principal diagonal. For example, if the entries above the main diagonal are all positive, then those below the main diagonal would have to be all negative. Or we could throw some zeros in there. Since 0 equals -0 is the case, then I don't need to get too carried away with positives and negatives. Zeros are certainly an option as well. But we get this kind of relationship in terms of the signs. Square matrix with complex entries. Ooh. All right, so we ain't going to deal a whole bunch with complex numbers. Of course, they pop up when we look at eigenvalues at some point, but we tend to shy away from them as entries of matrices and entries of vectors, though here's a situation where they're using complex entries in a matrix. We could do most all of this stuff with complex numbers as well. Matrix with complex entries is called Hermitian or self-adjoint. You dealt maybe with the adjoint of a matrix in sophomore linear algebra, maybe if you got that deep into the matrix theory. I prefer the term self-adjoint to the term Hermitian, but that may just be me. In functional analysis, these ideas come up, and the word self-adjoint for linear operators is a common term. Hermitian is not an uncommon term. I'm stepping out on a speculative limb here. I think that's more of a term you'd see maybe in the physics setting, Hermitian, than in a math setting. I prefer self-adjoint. We're going to deal minimally with this, but there's the terms. And the condition is A sub ij equals A sub ji conjugate. So a little bar here means, not to be confused with the bar we had in section 2.3, which meant mean and average. Here, we're talking about the complex conjugate. So we look at the ij entry, go to the corresponding ji entry, still considering square matrices here. We don't have equality there. We've got this conjugate thing. So if you'll take a matrix A, transpose it, and then throw some conjugates in certain places, we get this condition of self-adjoint satisfied. Why you would want that, I don't think we'll actually explore that in this class. Take a functional analysis class, which we have, Math 5740, which we occasionally run over the summers. But there's some different types of symmetry, skew symmetry, self-adjoint, some sort of conjugate transpose relationship there in the self-adjoint stuff. If all the entries of a square matrix are 0 except for the principal diagonal elements, then that matrix A is called a diagonal matrix. Same thing you had in sophomore linear algebra for diagonal matrix, ain't it? Non-zero entries off the diagonal? Yeah, exact same, because we said square matrix. Okay, so diagonal matrices are only defined when we're dealing with square matrices. The principal diagonal actually was defined whether we had a square matrix or not, and these are the differences in this class and what you might see in linear algebra. But that's kind of old news. Here's a couple of new ideas, and there's just loads of definitions in this section. If all the principal diagonal elements are 0, then a matrix is said to be a hollow matrix. Okay, so now we got zeros along the principal diagonal. If all the entries except the principal skew diagonal elements of a matrix are 0, the matrix is called a skew diagonal matrix. Okay, so it's got non-zero entries only down the skew diagonal from the upper right to the lower left. Skew symmetric matrix. Okay, skew symmetric, that's where we had a sub ij equals a sub ji with a negative thrown in. If we have a skew symmetric matrix, then there's no constraints on these i's and j's except they be between 1 and n. If they're the same, if we set j equal to I, we get a sub I equals negative a sub I. That'd be the diagonal entries. Well, the only way that can be satisfied is when a sub I is 0. So if we have a skew symmetric matrix, we must have zeros along the main diagonal. Such a matrix, by our definition here, was called a hollow matrix. So skew symmetric matrices are hollow matrices. Okay, some more definitions, of course, probably some new ones to you as well. And I doubt you saw this stuff in sophomore linear algebra. An n by m matrix A, for which the absolute value of a sub I is greater than the sum from j equals 1 to m, except for j equals I, of the absolute value of a sub ij, where this happens for all values of I as appropriate, is called a row diagonally dominant matrix. All right, so here's what that means. The entry, so think of it with think of this equation with a fixed I value, and then we're requiring this to be true for all values of I. Fixing I, that's what looking along a particular row. This is called row something something. So for given I value, what we're doing here is fixing I in this summation and letting j run from 1 to m, except for j equals I. So what we're doing on the right-hand side is summing up the absolute value of all the entries in the ith row of the matrix, except for the one on the diagonal, except for the aii term. On the left-hand side, there's that diagonal entry. So what you're saying is the absolute value of the entry on the diagonal in this row is strictly greater than the sums of the absolute values of all the other entries, all the other j not equal to I entries in that row. And this happens for the first row, the second row, through the nth row. That is, the absolute value of the diagonal entry is larger than the sum of the absolute values of the other entries in the row. And we could do a similar type thing for columns. A sub j, j is greater than a sum from I equals 1 to n, except for I equals j of a sub ij. So here we're summing over a column, and it's the same type of idea. So these have their biggest entries per row, per column, respectively, on the main diagonal for row diagonally dominant and column diagonally dominant. Just straight up diagonally dominant, it's a situation where, say, A is symmetric, so it'd have to be square by our definition. Then row and column diagonal dominants are equivalent in this case, and such a matrix, that is, it'd be a symmetric matrix that says row diagonally dominant, is called simply diagonally dominant. I mean, diagonal dominance and row dominance is the same thing for such a matrix. We'll prove a little theorem about this shortly. Something that you likely did see in linear algebra is the idea of upper and lower triangular matrices. You like those. You went to great trouble to get matrices in an upper triangular form when you did the row reduction stuff, when you were solving systems of equations, for example. Likely you went for something beyond upper triangular when you dealt with systems of equations. If you did Gauss reduction with back substitution, that totally involved upper triangular matrices. I never liked it that much because you could do more row reduction and get a matrix that's both upper and lower triangular. Get a diagonal matrix to the best of your ability, depending on the numbers and the number of pivots. But you've seen these ideas before, no doubt. A square matrix such that all elements below the diagonal are 0 is called an upper triangular matrix. If all the entries above the diagonal are 0, then it's called a lower triangular matrix. Lower triangular matrix, not sure you probably did much with those. With the row reduction stuff from linear algebra, you preferred the upper triangular matrices. If we were to take a transpose of an upper triangular matrix, we'd get a lower triangular matrix. So maybe it popped up in that setting. Something a little new, notice this triangular stuff was only good for square matrices. If we have a non-square matrix, same type of story in terms of having entries below the main diagonal that are all 0, or if we have entries above the main diagonal that are all 0. Such a matrix is called trapezoidal. So we can have upper trapezoidal and lower trapezoidal. If it's not a square matrix, it still has a principal diagonal that runs from the upper left diagonally down. Now, it may run diagonally down and run out of rows before it runs out of columns, or it may run out of columns before it runs out of rows. But if you look above or below the main diagonal, principal diagonal, one of those is going to be trapezoidal in shape, and that's the reason it's called a trapezoidal matrix. Square matrix A, for which the elements are 0, except for the following: A sub I plus C sub K. For some small C sub K, where C sub K is chosen from these values here, is called a band matrix or a banded matrix. All right, you should actually read A sub I, comma, I plus C sub K. We're looking at entries near the diagonal. So I have a typo here. I'll get that corrected. We're looking at a sub I plus C sub K. So we're going along, and when C sub K is 0, we're looking at diagonal entries. When C sub K is 1, we're looking at entries 1 unit above the main diagonal, the principal diagonal. When it's -1, we're looking below. So these banded matrices are of the form: along the principal diagonal, we may not have 0 entries. I'm trying to find the non-zero entries. It's described in terms of where the zeros are. Well, I'm trying to talk about where they're not, the except stuff. Along the principal diagonal, we may not have zeros. Just above that, we may not have zeros. Just below that, we may not have zeros. Maybe W sub U units above the main diagonal, we don't have 0 entries, but everywhere above that we do. W sub L units below the principal diagonal, we may not have 0 entries, but below that we do. So what these banded matrices look like is we got a bunch of zeros, and that's somewhat of a recurring theme in these classes of matrices. We got bunches of zeros, except in certain places. Along the main diagonal and near it is the only place that we have non-zero entries. The value W sub L is called a lower bandwidth, and W sub U the upper bandwidth. So that's how far from the main diagonal we go with these non-zero entries. You know from your linear algebra experience that for computational reasons, it's good to have a lot of zeros in a matrix. I go a touch more informal and say 0 is your friend, because arithmetic's easy with zeros. All this matrix stuff is computationally less complicated if you got a bunch of zeros. And that's the reason we're defining different categories of matrices that have zeros here and there. So that's my motivation for considering this class of banded matrices. Banded matrix with lower and upper widths of 1 is called tridiagonal. It's got a principal diagonal, and then it's got potentially non-zero entries 1 unit up and down from that principal diagonal. Matrix is upper Hessenberg form if it's upper triangular, except for the first lower subdiagonal. Okay, possibly there's a homework problem on that. That's fairly specific behavior from a matrix. Anyhow, it came close to being upper triangular, and it presumably has lots of zero entries. Gentle states, the author of the book, that banded matrices arise in time series, stochastic processes, and differential equations. So I'll leave it to him to justify that. I've done some things with differential equations meet matrices, and I don't recall seeing any of this banded matrix stuff. And what I've done is really very much at an undergraduate level in terms of the linear differential equations I've fiddled around with. So it's probably me. Transpose matrices, I've used that term already probably, but here's a formal definition for it in this class. Same thing you have in sophomore linear algebra. For an n by n matrix A, the transpose matrix is the n by m matrix, A transpose, where we take the A sub ij entries and swap them for the A sub ji entries. You swap the rows for the columns. You're familiar with transposing matrices. If the entries of A are complex numbers, then the adjoint of A is the conjugate transpose. So this is that Hermitian thing we ran up against a while ago, sometimes denoted A super H as opposed to A super T for this kind of manipulation. Again, we're not likely to see much of this kind of conjugate transpose stuff because we're not likely to deal much with complex numbers. So loads of definition, not all of which we'll actually use. All right, so what we're going to do is put vectors into matrices and pull vectors out of matrices. You did that in linear algebra, didn't you? You're testing a collection of vectors to see if they're linearly independent. You put them in a matrix as columns and row reduced and looked for pivot containing columns. So you put vectors in a matrix. All right, so the following is they're almost like software commands that put vectors in matrices and pull vectors out of matrices and make vectors out of pieces of matrices. The constructor function, diag mapping Rn into R, n by n, remember Rn, so this would be vectors within components. Rn by n, this would be n by n square matrices. Of course, everything we're dealing with, well, almost everything, involves real numbers in here. Diag of the vector d1, d2 through d sub n. So it's a vector from Rn with n components, using little square brackets to indicate that, is a matrix, an n by n matrix, which has the entries from that vector along the principal diagonal and zeros everywhere else. Vec diag maps are n by m. Okay, that'd be vectors, excuse me, that would be matrices. It's similar to what we had up here. Matrices that are n by m into Rk, k being the minimum of m and n. Would be a little simpler if m equaled n. We'd be dealing with square matrices. But this is mapping n by m matrices into R sub k, that's R sub m or R sub n, whichever of those two is the smaller, as vec diag of A equals A11, A22, up through A sub kk. It's, I want to say it's the inverse of this diag operation. Yeah, if we had square matrices, then there's some validity to that. But what it's doing is it's running along and pulling off the entries from matrix A that lie along the principal diagonal and putting them in a vector. So this is taking entries and putting them in a vector. This is taking principal diagonal entries and putting them in a vector. This is taking entries of a vector, components of a vector, and putting them in a matrix as diagonal entries. So there's a certain inverse relationship between these two. Don't take that too literally because I don't think we got any sort of one-to-oneness going on, particularly with this one. So inverse is arguable. Okay, here we're doing a sort of a pasting together of vectors. we're taking our n by m, so we're taking an n by m matrix and mapping it into our nm. That'd be nm real dimensional space. So we're getting out a vector with nm components. Vector A, vec of A matrix, an n by m matrix, is defined to be, we need to figure out what they mean by this, A1 transpose, A2 transpose through A sub m transpose, where A1, A2 through A sub m are the columns of matrix A. So they've taken the first column of matrix A, written it as a row vector, comma, second column of matrix A, written as a row vector, and so forth. So what they're doing is making a single vector out of a matrix, and they're doing it by running along the first column, picking off all the entries, then running along the second column, picking off all the entries, and so forth. That's why they're getting a vector with so many components. That's why they're getting a vector in R in M, because they've taken the n times m entries in this n by m matrix and put them in one long, looks like they put them in a row vector. Okay. Any reason you'd want to do that? Well, we've defined a linear structure on n by m matrices. We can multiply them by scalars and we can add them together. So we can take linear combinations in matrices. Who's your favorite vector space? Rn. In a sense, there's only Rn if we're going to use real scalars. So I guess we could probably use this kind of operation to set up an isomorphism between this vector space of matrices and this vector space of straight up vectors. I mean, of course, it's the obvious kind of thing. You just need the notation to translate the matrices into the vectors and back. So that's where this kind of thing could be useful, for example. Whoops. Okay, next, I think we're doing something with symmetric matrices. What's this last one? Define vec H mapping m by n matrices into I'm creating a vector here. What they're doing is taking the first row and they move down and over to the diagonal entry in the second row, write out the entries of the second row, move down and over to the diagonal entry in the third row, and so forth. So what they're up to here is really picking out the stuff above on the main diagonal and above the main diagonal, the principal diagonal. Gentle restricts this to symmetric matrices. We could do this to any matrix. You're losing information when you do this to a matrix, unless it's a symmetric matrix. So that's certainly defensible to restrict it to symmetric matrices. I didn't quite write it up like that, but it's a reasonable thing to do. Yeah, so if you know you have a symmetric matrix, you don't need to keep up with all the entries. You only need to keep up with something like about half of them. As you can figure out the other half because it's a symmetric matrix. This m times m plus 1 over 2, that's how many, in a sense, independent entries there are in a symmetric matrix. That's how many entries there are on the main diagonal and above the main diagonal, say. All right, next we're going to partition matrices. Let's see quite a bit of this partitioning of stuff. It's not entirely new to you, but probably you haven't done much with partitioned matrices. If you've done graph theory, it might have popped up in passing when you deal with adjacency matrices, in particular with I think it pops up with bipartite graphs. But Gentle never really gives a formal definition of a partition matrix, which is unfortunate. He deals with partitioning a matrix into 4 pieces. But not something more general. And the idea is to take a matrix and cut it into pieces that are themselves matrices, to partition it. You're familiar with this when we dealt with augmented matrices, A augmented with vector B. It's given here when you did systems of equations, AX equals B. So Here's what Gentle has, what our textbook has in terms of partitions. It's easy enough to see how this could be extended to a more general setting. But we're taking an n by m matrix A and we're partitioning it into 4 pieces. Capital A sub 1, 1, capital A sub 1, 2, capital A sub 2, 1, capital A sub 2, 2. Very reasonable notation. You might think in terms of minor matrices. You dealt with minor matrices when you define determinants in linear algebra. Where, and there's a bunch of verbiage written out here, and the restrictions are, what you're getting here with matrix A is the first row of matrix A is the first row of matrix A sub 1, 1, followed by the entries in the first row of capital A sub 1, 2. Similarly for columns. The dimensions have to work out right so that there's no gaps between these things. So I'll leave it at that. That's what all this story is here about how you find rows and columns of matrix A, what they are specifically. You know, there are probably 4 cases down there. When I look at rows, well, I've got the case where we have rows between here and here, columns between here and here, followed by columns between here and here, versus rows that might run through A11 and A12, then followed by rows that will run through A21 and A22. That's what all this stuff is. So it basically describes how the partitioning is done, and the dimensions are required to be such that there's no gaps in this. So the number of columns of matrix A11 has to be the same as the number of columns of matrix 2,1, and a similar type condition on rows running across. Okay, talk about sub-matrices. It's different from minor matrices that you dealt with back when dealing with determinants. Matrix B is a sub-matrix of matrix A if B is obtained from A by deleting some of the rows and some of the columns of matrix A. Okay, when you dealt with minor matrices, it was something like that. Minor matrices, you deleted 1 row and 1 column, which was probably how you computed determinants in linear algebra. Here, you're deleting some number of rows and some number of columns of matrix A to produce this matrix B. So this submatrix, when I go looking for submatrix B inside matrix A, well, I don't necessarily find all those entries clustered together in one spot. I mean, we could have cut the thing up in pieces in a complicated way. So I don't expect to see the entries of B, I want to use the word adjacent to each other in matrix A. It depends what rows and columns have been deleted to produce that matrix B. A square submatrix whose principal diagonal elements are elements of the principal diagonal of matrix A is called a principal submatrix of A. All right, so what you've done here is the diagonal elements of matrix B are the same as are elements that lie along the diagonal of matrix A. And also you're requiring that these little matrices be diagonal. So we don't have that odd thing about talking about principal diagonals of non-square matrices. But principal submatrix, we've got a question coming up about principal submatrices. Principal submatrix B obtained from an n by m matrix A such that if column J is eliminated from A, then the columns J plus 1 through M are eliminated in producing B, and if row I is eliminated from A, then all the rows following it are also eliminated. It's called a leading principal submatrix. All right, that means you've taken matrix A, you've gone to the upper right, and you've kept a little subsquare, because what you've done is you've gone over some amount, you've eliminated a column. When you eliminate that column, you eliminate all the columns after it. So you've wiped out kind of a right-hand part of matrix A. You've gone down and picked some row, eliminated it, and eliminated all rows below it. So you've taken matrix A and you've cut it in such a way that you've kept a little square piece of it from the upper left-hand part. Well, then the principal diagonal of B and the principal diagonal of A, they'll overlap. This is a case where you can find that submatrix with all the entries adjacent, as it were, in matrix A. So what a leading principal submatrix is one for which you just kept the kind of the upper left-hand corner of matrix A. Informally, formally, there's what it is. Okay, theorem 3.1.1 says, suppose matrix A is diagonally dominant, that thing about summing the non-diagonal entries across a row or across a column. So by saying simply diagonally dominant, the setting is that matrix A is a symmetric matrix, and it's both row diagonally dominant and column diagonally dominant. We only need to show one of those if we're given that it's a symmetric matrix to draw the conclusion of diagonally dominant. Suppose matrix A is in that sense diagonally dominant. If B is a principal submatrix of A, then B is also diagonally dominant. All right, so this will be an adventure, as are many proofs in linear algebra, and dealing with indices in the matrix. But if you can see the definitions, think what it means. In matrix A, if we go to any row, the absolute value of the diagonal entry in that row is bigger than the sum of the absolute values of all the other entries in that row. That's what diagonally dominant was. That's what row diagonally dominant was. What's going to happen in principal submatrix B of A? Well, the diagonal entries of B are also diagonal entries of A. So I'm not surprised that when I look at the diagonal entry here and I look at a row of this matrix, matrix B, we get that same kind of behavior because, hey, all the diagonal entries of B are diagonal entries of A. That's what a principal submatrix was. And what about the entries in the rows of B? They're the same as the entries of the rows of A? Not necessarily, but they include some of the entries in the rows of A. Maybe some of the others have been deleted. Remember, submatrix means deleting some rows and some columns. Principal submatrix means that's done in such a way that the diagonal entries of B are also diagonal entries of A. All right, so if we've got those big diagonal entries in A, yeah, I suspect we'll have big diagonal entries in B as well. So there's informally, wink, wink, how to think about it. If you can absorb the terminology, this ain't a shocking result. So let's go through proof. All right, so it's a matter really of trying to write it up and maneuvering through this stuff with all these indices. All right, so we're trying to show B is diagonally dominant. So we're trying to show that B is symmetric and let's say row diagonally dominant. Column diagonally dominant will follow if we've got a symmetric matrix. Definition of diagonally dominant. Okay, so let A, matrix A, be symmetric and diagonally dominant, and let matrix B, have the entries say B sub KL, be a principal submatrix of A. We need to show that B is symmetric and row diagonally dominant. You don't like that, then we need to show B is symmetric and column diagonally dominant. We got to show one or the other, row or column diagonally dominant. Let's do row. Okay, inherent in some unstated things are matrix A is a square matrix. So we only talked about symmetry for square matrices. So matrix B will be a square matrix as well. I mean, we're going to show it's diagonally dominant. So that's part of the deal in terms of the being a principal submatrix. Okay, so how about the symmetry stuff first? Consider entry B sub KL in matrix B. Well, B sub KL equals A sub IJ for some I and J in matrix A. So what we're going to do, here we are Pretend you're above the diagonal, above the main diagonal of matrix A somewhere, or matrix B, and we found this little entry B sub KL. We're going to move back to the left till we get to the principal diagonal, and we're going to move down till we get to the principal diagonal. How's that going to work? If we take B sub KL, all right, so this is the kth row and lth column. Let's look at the entry B sub KK. Also in the kth row and the kth column. If this actually is above the main diagonal, then L is bigger than K, and we've moved from entry B sub KL to the left to entry B sub KK. If this really is above the main diagonal, principal diagonal, then to get from B sub KL, we've moved down to the diagonal to get to entry B sub LL. Okay, if this is below the main diagonal, it's kind of a mirror image of that idea. But what we're doing is taking this entry, if we were already on the main diagonal, then this is a short conversation, but we've wandered along the rows until the row containing this B sub KL until we got to the main diagonal, principal diagonal, and we've wandered along the column L, the Lth column, until we got to the principal diagonal. So that'll give us the entries B sub KK and B sub LL. These are on the diagonal of B. We know B sub KK equals A sub II, same type of argument, and B sub LL equals A sub JJ, same argument, same I and J that we have up there. Also, we knew these entries on the principal diagonal of matrix B were also somewhere on the principal diagonal of matrix A. That's the principal submatrix property of matrix B. Okay, so when we make submatrix B, neither row J nor column I of that matrix were eliminated. I mean, that's where these things come from. A is symmetric. We've got A sub ij equals A sub ji. In this argument, we've shown if B sub KL equals A sub ij, then A sub ji equals B sub lk. Inverted or interchanged. The indices in both of these, you know, A sub ij equals A sub ji. You were given that A is symmetric. So we get B sub KL equaling A sub ij is the same as B sub lk equaling A sub ji. We get that kind of equality, and we see that matrix B is symmetric. All right, so you got the symmetry stuff down. There's pictures and geometry behind all of this. Now we want to show that row diagonal dominance stuff. So take a B sub KK, take a diagonal entry, so we'd be in row K. It's going to give a row argument here. B sub KK and B along row K of matrix B. That corresponds to some A sub I, a diagonal entry in matrix A. All right, so the kth row of B corresponds to the ith row of A. Then we know that in absolute value, B sub KK equals A sub II. I mean, even without the absolute values, they're equal, but I want to talk absolute values. Hey, you know matrix A is row diagonally dominant. So that diagonal entry of matrix A is strictly greater than the sum of all the other entries in row I of matrix A. That is, sum from j equals 1 to whatever's appropriate. We're given dimensions, sum from 1 to whatever. And so we're moving along the entries in the ith row of A, skipping over the diagonal entry itself. All right, why is that? Definition of row diagonally dominant in matrix A. Why, that's greater than or equal to the sum from L equals 1, except for K, up to M prime. M prime is whatever appropriate upper bound we have in matrix B of absolute value B sub KL. Why is that? because these entries in the kth row of matrix B are all included in these entries in the ith row of matrix A. Greater than or equal to, yeah, I'd kind of half expect a strict greater than. I'm not going to have entries of 0, so I can't jump that far. But there's more stuff here than there is here because we're dealing with a minor matrix. This includes some of the entries in the ith row of A other than the diagonal entry. So when I take the sum over here, we get something that's smaller or equal to this sum. And the punchline then is, hey, the absolute value of B sub kk is strictly greater than the sum of all the other, that is non-diagonal, entries of row K of matrix B. That's row diagonally dominant for matrix B, since K was arbitrary. So B is row diagonally dominant as claimed. Okay, so there are pictures behind this first part. The second part is just a simple little algebraic manipulation. Get used to this fiddling around with the indices stuff in matrix theory. That's how matrix theory works. Be a lot of this stuff with the indices that pops up. Back to the notes, a little bit more stuff. We'll take a break here, break up the video. A partition matrix is called a block diagonal if it's of the following form. So what they indicate here is they've got these matrices, A1, A2 through A sub k, along, in a sense, the diagonal. And all these zeros represent appropriate sized matrices of zeros. The zeros represent sub-matrices of all zeros of appropriate dimensions. So there's no gaps. You know what I mean? There's no gaps between the rows and columns here. So you've placed these matrices A1 through A sub k along corner, kind of lower right corner to upper left corner, and built a box out of them and put zeros everywhere else. That's called a block diagonal matrix. You like these? Yeah, they got lots of zeros in them, presumably. So that's why this even comes up. We could, similar to that diag function that we had above, that would map us from a vector into a square matrix. It took a vector and placed it along the diagonal. We could define an operation, diag, that takes these matrices and puts them in. What's the domain of this function here? I don't know. Nobody said these matrices had to be the same size. So we're getting k tuples of matrices of different sizes. Nobody said they even had to be squared, did they? Yeah, nobody said that. It appears that I think we'll most likely use this in the square matrix setting though. Oddly enough, we've only touched on this. This is the algebraic properties. So we'll take matrices and add them together, component-wise, entry-wise, we called it a while ago, multiply by scalars, entry-wise. Some resulting properties of that. Don't have any interest in going through this. You probably did it. You should have done it in linear algebra. You get commutativity of matrix addition, right? Maybe emphasize again. We're only looking at matrix addition and scalar multiplication. We're only looking at vector space type operations here. We get commutativity of addition. We get associativity of matrix addition. There's an identity. The zero matrix is an additive identity of appropriate dimensions. We get distribution of scalar multiplication over matrix addition. We get distribution of scalar multiplication over scalar addition, and we kind of move those scalars around. Associativity of scalar multiplication, as it's called in this reference. So no surprises there, stuff you're totally familiar with, stuff you hopefully proved a little bit of it in linear algebra. Yeah, there you go. We've got ourselves a vector space. So if we take all n by m matrices, we got ourselves a vector space of dimension n times m. As a note, not entirely ready to prove that because all we proved is what's dealt with vector spaces where the vectors were vectors in Rn. we'd have to do a little manipulation to take these matrices and write them, you know, as vectors in Rn. And we had a function that would do that. A subspace of this vector space is, say, the space of symmetric matrices. So we get subspaces of these. Here I've got n by m matrices. Here I've got n by n matrices. All right. The subspaces have to be made out of the same kind of vectors the big space is made out of. So I have to deal with that. And probably the word isomorphism should be tossed somewhere in here. And one of the exercises deals with showing some things related to symmetric matrices and these subspaces. An operation that I'm no linear algebraist, but what they're doing is they're adding a constant to all the entries of a matrix. Possibly there's some statistics applications for that. It's taking a scalar A and adding that scalar to all the entries of a given matrix and writing it as matrix A plus scalar A. I don't like the looks of that because you're adding matrices and numbers, and that bugs me. We could multiply, maybe introduce a matrix of all ones of appropriate dimensions and make a little more sense out of this. But this is some notation you'll see in the textbook where they add a scalar to a matrix. They mean add it to each of the entries of that matrix. Just like with vectors, if all the elements of a matrix are positive, we'll write matrix A is greater than 0. We did the same thing with vectors. I didn't care much for that either, but that's a notation that'll be used in this reference. If all the elements are non-negative, then we'll do, you know, an inequality type thing, A greater than or equal to 0. Something you may have touched on, or maybe not, in linear algebra is the trace of a matrix. So here's something we'll do a little bit more of in this class than in linear algebra. The trace of an n by n matrix is the sum of the diagonal entries. Can't argue with it. That's their definition. Easy enough to find. Well, you do a lot worse things to a matrix than finding the trace. The trace is easy to find for a matrix. Add the diagonal entries together. Had to be a square matrix, by the way, to keep an eye on when we are and aren't dealing with square matrices of necessity. Some properties of the trace. Trace of A equals a trace of A transpose. Sure, because the diagonal entries of A and the diagonal entries of A transpose, they're the same. It's a square matrix, remember. The trace of C times A is C times the trace of A, a piece of cake. That's just distributive property of addition, right? You want to prove that, you put a C in front of the matrix A, you get a C in front of all these entries, you factor it out, and there you go. So no surprise with that one. Trace of the sum is the sum of the traces. Yeah, well, a trace is a sum. So I'm not surprised that a sum is a sum of two sums. So there's some commutativity of addition of real numbers going on in that one. None of these are surprising. Next topic, let's say for a second video for this section, is determinants. So this is a big deal. We'll use determinants when we find eigenvalues and eigenvectors, for example. We're going to approach determinants probably, definitely, you didn't approach it the way we're about to in linear algebra. In linear algebra, you likely approached it with a recursive definition. We're going to approach determinants using, of all things, permutations on sets. We're going to step aside and do a little bit of stuff from Introduction to Modern Algebra and talk about permutations and the sign of a permutation, and some symmetry groups will pop up. I mean, it's just senior level algebra stuff to you kids. But we'll go through and define determinants next, and we'll do it in this different way. And when we prove things about determinants, we will have to prove them using this particular definition. This permutation stuff, I think, is sorely missing from Gentle's book, but I've got another reference we'll go through, and I've got everything in the notes. So I will see you shortly in part 2 of section 3.1.